Yeah, so thank you and welcome to this last talk this evening. I think there will be a film at 0 o'clock, but the last talk for this evening is from Maxwell to antenna arrays. You probably all know Maxwell's equations, the 4 equations. I actually like the idea that with 4 more or less simple equations you can really explain a lot of stuff. And I'm a communication engineer, so I will stay in 3 dimensions. Back when I was studying, I actually also visited a lecture about relativistic electrodynamics, which is all this Maxwell in 4 dimensions. And I passed it somehow. But yeah, what you can see here on this nice picture is a AM broadcasting station with an AM antenna array. I think it was medium wave here in Brazil. It was, I think, in Rio or Sao Paulo. I was more working with stuff like this. At the moment, I work as a science journalist. And it's quite interesting how a lot of stuff like mobile broadband and also things like radio astronomy are coming together in the field of antenna arrays. So I will get the topic to this. And also, I think for everybody, some fundamentals of wave propagation and how antennas are working, which now everybody has in his or her pocket, is very handy in many situations. So, here are our 4 Maxwell equations. We have Gauss' law, we have Gauss' law for magnetism, we have the law of induction, Faraday's law of induction. Oh, I think, could it be that this microphone is on? No? Okay, good. And the 4th one is Ampere's circuit law here. A bit more details. So Gauss' law of induction actually describes the relationship between a static electric field and the electric charges that cause it. So here we have 2 points of charges, and the static electric field points away from the positive charge on this side here towards the negative charge. And very easy example is a capacitor. You all know this. You have your two sides of the capacitor where the charges are, and then you have the electric field in between. A little bit of mathematics. So here we have this nabla operator with the c dot is the divergence of a vector. It's the derivative of each value in space, so in x, y, and z coordinates, and then they are added up. So actually this measures the magnitude of a vector, field's source or sink at a given point. And if we later come on to free space propagation, this rho here, so we have no charges in free space, so this rho becomes 0, and we can simplify this equation. So the next one, Gauss' law for magnetism, is the divergence of the magnetic flux density equals 0. That states that there are no magnetic charges or magnetic monopoles. You all probably know what happens if you break a magnet into 2 parts. So you got 2 magnets with a plus and minus pole. This equation states that the magnetic field lines, so the circles here, neither begin nor end, but make loops or extend to infinity and back. The 3rd one is Faraday's law of induction. This one describes how a time-varying magnetic field creates or induces an electric field. This lengthy term here is the curl of a vector. This actually describes the direction, so it's the direction which is like orthogonal to the other ones. A good example is where this law is working is an electric generator. So for example, it has a rotating bar magnet which creates a changing magnetic field, and which in turn generates an electric field in a nearby wire. So you get your electricity by moving your magnetic field. And the last equation here is Ampere's law with Maxwell's addition. And this one states that magnetic fields can be generated in two ways. One way is by electrical current, and this was the original Ampere's law. And Maxwell's addition then added that also by a changing electric field, a magnetic field can be generated. And this addition, so this is this part here, like the E field, the electric field, derivated to the time, so the change of the electric field. This is especially important because it shows that not only does a changing magnetic field induce an electric field, so this was the law of induction, but also a changing electric field induce a magnetic field. And therefore, these equations allow our self-sustaining electromagnetic waves to travel through empty space. So on a whole, we have those four equations. Please keep them in mind for a moment. I will come back to them later. First, some history, because it's exactly 150 years ago that these equations, or Maxwell's paper, a dynamical theory of the electromagnetic field, were accepted for publication by the Royal Society. Perhaps some remarks what was going on about technology at this time. So here the average lifetime of a light bulb at 1870 was around 10 hours. The first central station providing public power is believed to be one at Gadam, Surrey in the UK, and it was switched on in 1881. So probably Maxwell didn't have electric light when he wrote this paper. There was also a lack of mathematical fundamentals. So already Faraday, who was also researching a lot in this field, envisioned in 1830 a mysterious, what he called a mysterious invisible electronic state surrounding the magnet, what we would today call a field or a vector. But vector calculus was not invented yet. Faraday also hypothesized that light itself was a magnetic wave, but shaping these ideas into in a complete theory was way beyond his mathematical abilities. So actually, Maxwell also didn't have 4 equations, but he had 20 equations. So you can see some of them here on the right side. And it took another 20 years until they were understood by someone else. And it was this actually self-taught British engineer, mathematician, and physicist, Heaviside, who put the equations then in their present form, to these 4 equations. Some years later, Heinrich Hertz, brought the experimental proof of Maxwell's theory. He verified that electromagnetic waves exhibit light-like behavior of reflection, refraction, diffraction, and polarization, and also that the speed of light and that of electromagnetic radiation seemed to match up pretty well. So the proof came up that light also is an electromagnetic wave. So back to Maxwell's equations. If we come to free space propagation, in a vacuum we have no charges and we have no currents. So this rho here in Gauss law equals 0, and the J in Ampere's circuit law also equals 0. So the equations simplify to this one, which looks pretty symmetric, except here's a minus and here are this permeability and permittivity, which can be summed up to the speed of light here, c. When we then want to come from those equations perhaps to something that looks more like a wave, like we know these waves are like a cosinus or sinus. What we do is we take the curl of the curl equations. I put those Maxwell's equations here to the side. I will show it here for the law of induction, for the E field, electric field. For the magnetic field, it actually works the same. So we take the curl of the curl equations here, do some vector calculus. So the curl of a vector equals, this one is the gradient of the divergence of a vector minus the square gradient of this vector. Then we come to this equation here. Here our divergent, we see this up there, equals 0, though all this stuff equals 0. And this part here pretty much looks like this part here, so we can change this. Actually, the beamer is stealing some lines, I think. So this is also a division here. And we end up in, then we put this to the other side, and we end up in those who are called the wave equations. These are still two partial differential equations. The simple solution of those equations is a plane wave, which then you can see here, or something is happening here. Yeah, and they are already pretty much looking like waves, like we get here our amplitude, here the E0, we get a cosinus like the waveform, then we get our omega like the frequency, depending on the time. The k here is the wave vector, and here we get our dependence on the location and the phase. This wave number k actually represents the rate of change of the phase and is also pointing in the direction of propagation. A plane wave can be seen here, for example. So we got a E field and an orthogonal magnetic field. Plane waves are defined like to have a constant frequency. The wave fronts are parallel planes of constant peak-to-peak amplitude, and all this and normal to the phase velocity vector. And such a plane wave always have a pointing vector. The S here, the pointing vector, represents the energy flux density of this wave. And is also in the direction of propagation, which is always orthogonal to the two fields, to the E and the B field. Then every wave has a polarization. The polarization is defined as the alignment of the E field, the electric field. So here, for example, we have a horizontal polarization. And we have a linear polarization here, because we have only parts in one direction. There are also other forms. For example, here you can see a circular polarization. This occurs when we have two orthogonal E components with exactly the same amplitude, which are 90 degrees out of phase. And those two waves actually then behave like a wave circling around. For example, here is an antenna which can be used to receive a circular wave. It's called a QFH, a quadrifilar helicoidal or something like this antenna. And I built this one for receiving like some NOAA weather satellite pictures which are sent out in FM. And it's kind of very cheap to build this antenna with some waste pipe, some copper cabling, and the receiving can be done, for example, with a really cheap software radio, such an RTL, SDR. And with this, you can see Europe kind of from above. I can show you one one picture, which is also not so good on the beamer here. So this is the RTL SDR. This is this QFH, circular polarized antenna in the countryside. Here we get some open source software for receiving the signal. The program is called GQRX, which is really does nice FM demodulation. And then there's a program to calculate from the signal the satellite picture, which, it's just an FM modulated signal. And here, for example, there are a lot of clouds. Here, this is Italy, like the boot of Italy can be seen here. And here's this is the Mediterranean with some clouds, and this is kind of here Central Europe. So with kind of 20-25 euros, you can just see Europe from above. So if you have some spare time, you should really go out and hunt for some satellites. But back to some propagation first. So we got the vertical and we got the circular polarization. There's also elliptical polarization that comes up if you got also two components like the circular polarization, but they have different amplitudes. So we don't have the circle, but the elliptic, I don't know. Regarding polarization, if you want to receive, for example, a horizontal polarized signal with a vertical polarized antenna, you always lose some signal power. Or for example, if your circular antenna is circling in the wrong direction of the signal, you got something. It also depends on whether you are indoor, outdoor, because every reflection and all the scattering and stuff also manipulates your signal, so you don't only have a vertical component. But often it makes sense like to move the antenna a bit if you have bad signal, or in many modern equipment you have like two receiving antenna that do some kind of receiver diversity to get both components of a signal. If we take a look on free space propagation in the real world, we assume we have a certain distance between the transmission antenna and the receiving antenna. And it's good to assume that this distance exceeds the antenna length and also the wavelength by several multiples. Because in this case, your pointing vector, like the S from before, seems to radiate from a single point, and we can use the Fraunhofer far-field approximation, just called, which simplifies a lot, because we can divide our term of propagation, like the point, the energy flux density here, in a spherical propagation part. So you can, this can be seen in the figure here. We can divide the propagation, the area on a sphere grows. So here we get a small area, and then if we move farther away from our transmitting antenna here in the middle, the area on the sphere grows proportional to the square of the distance. And at the same time, if we use the density, this one drops inversely proportional. So this behavior is the 4pd square in this part. And then we have the three-dimensional profile coming from the antenna pattern. So on the whole, this becomes quite easy for propagation. We also know that higher frequency do not reach as far as lower frequencies. And this is caused by the antenna aperture, the A. here equals the pattern GR, the antenna pattern GR, and here lambda square, our wavelength, divided by 4p. And the antenna aperture determines how well an antenna can pick up power from an incoming electromagnetic wave. And at higher frequency can be seen like that the antenna in proportion to the distance is smaller, and therefore we cannot pick up as much power. And then, yeah, we can put in here, no, that's afterwards. Then at the receiver here, we get the power PR. And this equals the energy flux density, which is like the wave in the free space, multiplied with the antenna aperture. Then we can put all the stuff here, the S and the A, in here, and we got this term for our receiving power at the receiving antenna. Now dependent on the distance and also on the frequency. And then one term which is often used is a Free's transmission equation that defines the ratio of power available at the input of the receiving antenna to the output power of the transmitting antenna. And here the inverse factor of this equation is called the free space loss, which is actually the minimum loss you always have if you have two antennas sending around something. Mostly you get additionally reflections, diffractions, attenuations from the atmosphere and so on. But yeah, this is the minimum loss you have. When it then comes to antennas, we always like these antenna patterns because they describe like how much of the energy is sent in which direction. This pattern depends on the current distribution on the antenna, because here we have mostly some metallic materials, so we get some current, so J isn't equal to 0. For example, here we get a half lambda dipole. The calculation of the pattern is then based on Maxwell's equation again. You normally work with a vector potential and everything in circular coordinates, and it becomes a bit complicated. So fortunately, there are a lot of nice programs who do the work for you. This here was calculated with 4NEC2, which is a really nice program. It's free, and I think it's not open source, but it's also for Windows, but it works also fine with Wine under Linux. It is based on the numerical electromagnetic code, which is the NEC here in between. And the code is based on the method of moments, solution of the electric field integral equation. NEC was originally written for the US military and is then put under public domain. It's a bit complicated to build your own antennas with this, so it's possible, but yeah, probably there are lots of very expensive programs which makes it easier. But the cool thing about this program is that it has many, many example antennas which comes along with the program. So, for example, also this QFH antenna I showed before for receiving the NOAA weather satellites was also already included in the examples. So here you can see the main window of the program. Then you can go here to calculate. Then you get this windows. Here you can choose, yeah, I want to calculate the far field pattern of my antenna. Then you can just go to generate, and then you get a nice you get 2D patterns, but you also get a nice 3D pattern. And for example, here it can be seen this antenna is for these weather satellites who are running like above you from horizon to horizon. So you want to have an antenna pattern which also goes up from horizon to horizon and which also does the circular polarization. So this fits pretty well. An important principle when it comes to antenna patterns is the interference between different signals. So if you get, for example, 2 waves, you always have there's always constructive and destructive interference. So, for example, when it comes to interference here, you can see swimming pool interference done by, I think this is a French astronaut who is doing this, like putting 2 arms in the water, and then the waves coming from 2 sides are interfering by each other. So we got some peaks of the water, and sometimes it goes down. Here, if we got 2 waves and they are in phase, so which means they are starting at the same time and location, they are causing constructive interference. And if those 2 waves are 90-degree out of phase, which can be seen here, you get destructive interference. So they cancel each other. And yeah, for anything in between, you also get some interference in between, which makes this resulting signal a bit smaller or bigger, depends. I also found this nice picture of 2 interfering waves coming from 2 points here on Wikipedia, so can take a deep look. Okay, thanks. A very descriptive antenna for explaining the interference stuff is the Yagi antenna. You can see here, for example, Yagi antenna built for the Freifunk wireless network, like to get a directional antenna for 2.4 gigahertz. You always got a driven element, which is this one in this case, and then you get some parasitic elements, director here, no, the directors are in front, and a reflector here in the back. The parasitic elements are receiving the signal from the driven element and at the same time also sending it out again. And they are not exactly resonant, but somewhat shorter or longer than our half lambda wavelength. And this creates a capacitive or inductive reactance. And this reactance modifies the phase of the element's current with respect to its excitation from the driven element. So you can see this, for this 2-element Yagi, we get the driven element and the emission from this element, and then we get the director, and the emission from the director is out of phase in such a way that here to the front of the antenna we got a constructive interference, so the signal is getting bigger, and to the back, the backward emission, we got a destructive interference, so we get less power to the back and more power to the front as wanted. What would, for example, happen if we connect all these Yagi elements here to a source? And then we could, for example, manipulate the phase of each element individually. So we can see this here. This is called then a phased array. Here, for example, we have a lot of small antennas. Then we have a phase shifter, so it's in German here. I only found this in German. And then by manipulating the phase of each antenna, we can change the direction of this array. Or the direction of propagation. Here is another example. We got two antennas. If we put signals on each antenna with the same phase, the main lobe of this array equals the main direction of each antenna. So it's going straight forward in this direction. In the other case, if we delay the phase of the upper antenna slightly, then the lobe moves up. The lobe of the antenna array moves up. And the gain of the resulting antenna always consists of the gain from each single antenna, and then there is an array factor. So if you have a lot of antenna, you can create very high antenna gains, and by manipulating the phases, you can then move the lobe direction as wanted. There are different techniques to do the phase shift. The first ones were in hardware, so you get just longer cables, for example. Carl Ferdinand Braun invented this technique in 1905. Then it was mostly used as often for military purposes. For example, it is still highly used in radar systems. It was later then also adapted to radio astronomy, leading also to a Nobel Prize for Physics for Anthony Hewish and Martin Ryle for their interferometric radio antennas. But more on this later. An interesting thing is when you mix, or like some time ago, software-defined radio. This technique came up in a large scale. And if you mix this with antenna arrays, you get a really lot of flexibility into this phased arrays. You can, for example, manipulate the phase of each signal in software. You get a very flexible, for example, beam forming. Depending on the phase you set in software, you can change the direction of the beam. And also mix this with MIMO techniques. So with MIMO, multiple input, multiple output, you additionally do some precoding on each signal coming from each antenna. And with this precoding, you try to take advantage of the channel properties. For example, in a very scattering environment, a channel has a lot of different uncorrelated paths. So you can increase the data rates. For example, it's also used within the newer Wi-Fi standards. It's also getting cheaper, so not only the militaries can use it now, also like for mobile broadband. They are doing a lot of research at the moment, for example, for 3D beam forming. This can be seen here in this picture. So we got our base station, then we get one beam here down and several beams to the skyscraper here. And the idea is, for example, to cover different levels of a skyscraper with different beams on the same frequency. So they are always afraid how they shall transport all those data, those mobile data, so they can actually reuse frequencies with this beam forming. So the latest headline came from ZTE and China Mobile, who did a test with the 2D arrays with a total of 128 antennas. As I already told, this software phased array technology is also used in radio astronomy. There it's for receiving signals. And that's also very general. An antenna always behaves the same, no matter if it's used for transmission or reception. So also, you need a really precise timestamp of each signal on each antenna, and then you can process the signal from the different antennas with different phase shifts, depending on which direction you want to receive the signals from. And yeah, you can get a really good antenna gain by using a lot of antennas. And there it's also important to distribute them on a long array. The radio astronomers actually have the problem that to explore signals at lower frequency, the telescopes need to be really, really big to have a good resolution. And it becomes quite unhandy, like if you see the dishes, they already started building these dishes in valleys, but then it becomes quite unhandy, like if they want to get a signal from another galaxy, which is not right above the dish, but at some other location. So it's just not possible to move it anymore. The angular resolution of a telescope here depends on the wavelength divided by d. d is either the diameter of the telescope or it's the baseline, so the length of the maximum physical separation of the telescope in the array. And a nice example is, for example, the LOFA, the low frequency array, because they want to observe radio frequencies from 10 to 250 megahertz. So you got really kind of long wavelengths from 30 to 1.3 meter. So what they do, they build a lot of different stations and distribute them over half Europe. In a total, it's around 25,000 small antennas, concentrated in 48 large stations. They are also still building new stations. I think the last one was in last summer. They built the latest station in Germany near Bremen or Bremerhaven, something like this. Within LOFA, the angular resolution goes down to 0.21 arc seconds, and the widest baseline is something like 1,000 kilometer, and at the highest frequency. And if you build such stations in software, it's also built with the software radio technology. Also, the data processing becomes quite interesting. Because perhaps you remember, you got your audio CD, you get 80 minutes of music, you get around 700 megabytes of data. You can hear from 20 hertz to 20 kilohertz, so you get around 20 kilohertz audible bandwidth. Nyquist told us that we need the double sampling rate, so we often use the 44.1 kilohertz, 16-bit and 2 channels. Here we got frequencies from 10 to 250 megahertz, which makes a quite bigger bandwidth, and we got like 25,000 antennas, which all generate a lot of data. What they then do is they do a kind of pre-processing of the data at the station already. Like they have to decide before which direction they want to get the signals from, and then they do this correlation of the signals already partly at each station, and then they send the data to the Netherlands, to Groningen, where a Blue Gene supercomputer does the final processing from the distant stations then. This LOFA telescope is also a pathfinder project for the square kilometer array. This one is in pre-construction phase at the moment. It's planned to be built in Australia, a part, and another part in South Africa. The plan is to cover a frequency range from 50 megahertz up to 14 gigahertz in the first 2 phases of the construction. So here you can see an animation, it's not really built, of the dish antennas. In phase 1 shall provide 10% of the total collecting area at low and mid frequencies by 2020. By 2020, and phase 2 then shall complete the full array at low and mid frequencies by 2025, and then phase 3 shall go up to 30 gigahertz. It's actually 3 telescopes because of the huge bandwidth. So 2 dishes. Here you can see the animation of one of the dish antenna arrays. And for the low frequencies, you get an array of dipoles. The maximum baseline of this antenna are 3,000 kilometers, and the collecting area is 1 square kilometer, therefore it's called square kilometer array. And within this project also the main challenge is the quite huge amount of data. I had an interview with the technical director of this SKA earlier this year, and he told that they are planning to have more data than the internet carries today altogether on their stations. And all this data has to be processed, transported, and made available for the scientists. They plan to deploy like fiber optic with a length that would reach around the world twice. And they actually trust in Moore's law to process all this data. They wait until they buy the hardware until, later, until it is really needed. The scientific goals of this array, this telescope, is, between others, the 21 centimeter hydrogen line that shall map 1 billion galaxies out to the edge of the observable universe. They will do research in the processes resulting in the galaxy formation, and evolution will be done, and research in the evolution of cosmic magnetic fields and the epoch of reionization after the Big Bang. But yeah, here all this stuff is again connected somehow to relativity, creation of the universe. So I will end here. Thanks for your attention. And if you have some questions, I can try to answer them.
Okay. Thank you. As always, there's 4 microphones, one there, one there, one there, one there. Just line up if you have any questions. Maybe you need a little refreshment on vector calculus. Maybe just want to know some physics. Just ask. Do we have questions from the internet? Oh, the internet is already asleep. Okay, go ahead.
When you were getting the images from the satellites, could you rely on good documentation, or was it a lot of trial and error?
No, there's actually kind of good documentation. In the internet, just search around for NOAA satellites and SDR. I also wrote an article about this in the Hardware Hacks, but it's not online, unfortunately, so you would have to buy the magazine.
Thank you. Thanks.
Okay.
Does the software you presented consider cases of non-free propagation? So if electromagnetic active medium is present in the near field?
This antenna software, I don't think so, actually. You can do like areas, what's the name? Flächenantennen in German. but I think it doesn't support like different materials of the surrounding space. But I'm not quite sure. So there's also a lot of documentation on the website from Fornec too. Perhaps better have a look there.
Thank you.
Okay. To the right, please.
Okay, in the plot with the Yagi antenna, where the field amplitude of the passive element was higher than the field of the amplitude of the driven element. I wonder how that could be. Is it magically producing some energy, or where did this bigger field size come from on that plot?
Yeah, from Wikipedia. No, actually it shall be smaller, because you always have some losses when the element receives and then again sends the stuff. So yeah, you are right.
Okay.
Yes. Yes. How do you deal with noise being generated by the antenna itself? Can you do other ways to actually lower the noise of the antenna itself, or are there other ways of making sure you have the maximum signal-to-noise ratio?
You mean in a phased array or in this Yagi, or what?
For example, or with the dish antenna, like in the later square kilometer array?
Oh, I don't know actually. I'm not so much into the technology. I think they have to deal with it because probably they will catch up a lot of noise. But yeah, probably, yeah, often your noise have some regularities, so you collect a large amount of signals and then you can kind of calculate the noise out. So that's how you normally do it. And yeah.
Okay, internet.
We have two questions here. One is intercontinental SSTV possible? And if yes, which type of antennas would they are needed to do this, and how big would these antennas be?
Intercontinental what?
Slow scan TV.
Yes.
Slow scale TV?
Yes.
Someone said yes.
On HF it's quite slow, but it's possible.
Okay, I actually don't know what slow scale TV is.
No. SSTV ist möglich. SSTV is possible. An HF. So intercontinental SSTV is possible. But you need time because it's extremely slow because of the low frequencies.
So you use this ionosphere stuff,
Yeah.
reflecting stuff
Definitely.
at high frequencies, yeah.
Okay. On
Thank
20
you.
meters. The right, please.
Maybe I missed something, but what is the connection between all this Maxwell stuff and the phase array stuff? Because this phase array you can use with conventional waves like ultrasonic or something. Where's the connection between? Is this really used for this phase array? This is only a superposition of elementary waves.
Yeah.
In the far field, so I don't see the connection to the Maxwell equations there.
So the Maxwell equations explain all wave propagation. So it doesn't matter if you have radio frequencies or light. So they are kind of explaining the wave propagation, and then I try to explain what you can all do with in different fields of this wave propagation and regarding to antennas.
But this what you use afterwards, it's not a property, or it doesn't use a property or a unique property of radio frequencies for this beamforming stuff. This is I see.
You can also do it with audio waves, for example. Yeah, that's right.
So okay.
Okay.
Is it on? Would it always be the case that I would need multiple receivers to make any use of a receiving array? Or could there be any way to use just one receiver with an antenna array and somehow calculate the direction?
so just if you just use one receiver of the antenna array, and to do what? To
I don't know if you wanted like a directional reception or something like that. Is it always the case that I need one receiver per one part of the antenna?
Yeah, you need some kind of construction that does the directivity. So you don't need an antenna array. There are also other forms of antennas which are directional. But within the array, like you need different signals to get these different phases, like to create your directivity. Then.
Please go to the mic if you want to say something, because the stream cannot understand you.
Well, for the case of antenna arrays, you don't need several receivers at every antenna part. You can also combine the signal and hardware with the phase shifters, like she said. And after you have combined the signal over some power combiners, you can just put it into one single receiver, but you have to do all those fancy phase shifting stuff in hardware, and that's harder than to combine the signals after you have digitalized them. Thank you.
Okay, thank you.
Any more questions? Okay, internet.
Yeah, I have one question about the Maxwell equations. And this question is the second equation meant as statement on a specific point or of the whole field?
On what? On a specific pulse?
On a specific point or the whole field?
You mean field?
A field, yes.
It doesn't need to be a point. So, for example, it's also if you got capacitors, you can have rectangular or whatever form of. No, this was the first one. What, the second?
Maybe just show the slide so we know what you're talking about.
So. It was the second equation, right?
Yes.
And then if it's 1 point or if it could be a field.
If this equation is meant as a statement on a specific point or the whole field.
Sorry, I don't understand.
It's a statement on the entire field. B is the magnetic field, not a magnetic point, which does not exist.
Thank you.
Technically, this is a statement about the sources of the magnetic field. So the second Maxwell equation just says that there are no sources for the magnetic field, which basically means there are no monopoles. Do we have more questions? Okay, thank you. Thank our speaker again, please.
So, thank you.